Alright, so this is section 4.2. I think there's 3 word problem sections in chapter 4, and there's only 5 sections in chapter 4. So it's a heavy word problem chapter. And quite honestly, I think the word problems are the easiest part of the class. So if I do a decent job explaining these, they shouldn't be that bad. And most of the word problems in this particular section I took directly from my Math 151 material. Maybe I cleaned up the words a little bit, but these are word problems that you may have seen in college algebra. In college algebra, since we didn't have the calculus to solve these problems, we sketched graphs on our calculators and got the answers from our calculators. But nevertheless, these are kind of college algebra level difficulty. So let's try to just kind of go through the problems. And I made a ton of parts for each of these problems just to kind of walk you through the solutions. So let me just read the initial paragraph or initial problem to myself. So campground owner has 5,000 meters of fencing. He wants to enclose a rectangular field with the fence that he has. Let W be the width of the field and L be the length of the field. That's not a question. Ultimately, the question is going to be, what dimensions of the field can he construct to get the maximum area enclosed? But I kind of walk you through that. So we'll do these one step at a time, and each step is just kind of a nice small, sliver of the problem. So usually when I draw rectangles, I make the shorter side, I call it the width, and the longer side that I draw, I call the lengths. But it's really not, that's not mandatory. You could have your drawing different than mine. Your lengths and your widths can be switched, and you could have drawn a rectangle like that. It doesn't have to be exactly to my rectangle, but this is my classic rectangle. I usually make the sides that are parallel. I don't even know how to describe those, but I make these sides the longer ones, those sides the shorter ones, and that's not crucial. The only thing the first paragraph or few sentences tells me is that there's 5,000 meters of fencing, and that's a linear number and not an area. So because this is a linear number, this 5,000 meters I'm going to use to construct the perimeter of my rectangle. And in general, the perimeter of any rectangle is twice the length plus twice the width. And specific to this problem, my perimeter is going to be 5,000 meters. And I'm going to hold off on plugging that 5,000 into the meters into my work, because it's just going to make the work too messy. So that's what the first paragraph or first few sentences allows me to do. It allows me to sketch what I'm trying to do. I'm trying to enclose a rectangular field with 2 sides that I'm going to call widths, 2 sides I'm going to call lengths, and the perimeter is 5,000. So 5,000 is 2L plus 2W. That's the beginning of this problem. Now I'll start just chipping away at the parts. Part A, write an equation for the length of the field. Well, I have an equation that describes this field, and when it says write an equation for the length of the field, I need an equation that says L equals, because it's implying that I need an equation solved for L that represents this particular field. Well, this is the only information I have for this field, so this is the equation I'm going to use to generate my answer to part A. And probably the easiest thing to do to get this equation is take my equation that I created before I got to any of the questions, divide everything by 2. That will give me 2,500 equals L plus W. And then I can minus W from both sides. And I could either write 2,500 minus W equals to L, or I could write minus W plus 2,500 equals to L. These would both be fine answers for part A. And usually you write the letter first and the number second, so that's probably the nicer way to write it. I almost like this better. I'm going to choose this version of it, but if you choose the bottom version, it's hardly that big of a deal. So I've gotten through the initial reading of the problem, which gave me my initial diagram, my perimeter equation. Now I'm just chipping through the question. So part A, write an equation for the length of a field. I created an equation that used the information in the original problem and created an equation, meaning a problem with an equal sign, that will solve for L. Part B says write an equation for the area of the Princeton region. Well, this region that I drew without any numbers on it, it's just a rectangle. And for rectangles, the area of any rectangle is the length times the width. And that's perfectly fine. This would be correct. This is an area for the Princeton region. It's length times the width. But that hasn't taken into any of the restrictions on the problems. So what I'm going to do with this equation is I'm going to change the L in that area equation to 2500 minus W. So as I do this, I'm writing an equation for an area. And instead of saying area is length times width, I'm going to say area is 2500 minus W times W, changing the length to 2500 minus W. And I'll clean that up. At least I'm going to clear the parentheses by multiplying 2500 times W and getting 2500 W, and multiplying minus W times W and getting minus W squared. Again, that's maybe, disconcerting to have the W squared second, but it's fine. It's going to make the math easier to do. All right, so done with part B, and hopefully that was followable. So for part C, it says I want to find the domain of this equation, and the domain will be of the form a number is less than or equal to width is less than or equal to some number, and those aren't the same numbers. They're going to be different numbers. And in order to do this, I have to understand the problem. If I have 5,000 meters of fencing and I have to construct two widths, I can't have a width less than 0. 0 would be the very smallest width I could have. Actually, you couldn't really even have 0. Maybe you need 0.00001 centimeters. But I'm going to say the width at minimum has to be at least 0. And then if I created two widths with the 5,000 meters of fencing, each could maximum be 2,500 meters, because if this side was 2,500 meters long and this side was 2,500 meters long, it would use all 5,000 meters of fencing up. So I'm going to say my width has to at least be 0. I can't build a fence that the width is negative. And if all I built was widths, then each width could use up half the fencing, and I'd have to make two 2,500 meter fencing. And this is going to turn out not to be very good. If you had a width of 0, you wouldn't get any area enclosed. Similarly, if you had your widths of 2,500, you wouldn't get any area enclosed, because you wouldn't, in this scenario, if the widths were 2,500, the length would be 0, and then length times width is area, and 2,500 times 0 is 0. If the width was 0, the length would have to be 2,500, and again, you'd get a negative or 0 area. So in this problem, I'm just logically thinking what can happen. You can't build a negative width, so the width has to be at least 0. And if all I built was widths, then I have 5,000 meters of fencing. I'd split it between the two sides, and I'd get 2,500 meters on either side. So that's the restrictions for this problem. You definitely can't make a negative width, and we don't have enough fence to make a width bigger than 2,500 meters. So that's the answer to part C. Now, part D, we're trying to find a maximum. We're actually trying to find an absolute maximum for this equation. So basically what I'm thinking of is finding the absolute maximum of the area equation between 0 and 2,500. And how do I do that? Well, that's what we did a lot in the last section. So to find the answer to part D, I'm going to take my equation, my area equal to 2,500 W minus W squared over the region 0 to 2,500, and I'm going to find the absolute maximum. And how do I find absolute maximums? I find the derivative. The derivative of A prime is going to be 2,500 minus 2w. After I find the derivative, I get critical numbers. I go 2500 minus 2w equals 0. I'm going to add 2w to both sides. That will give me 2500 equals 2w. And then I'm going to divide both sides by 2. And I'll get 1250 equals w. That's a critical number. Remember when we tried to find absolute maximums, we made tables. I took the x coordinates of the domain, or the boundary points, and put them in at my table. And in addition, because this number is between those values, I'm going to plug this in my table. So these are my x's, and these are my y's. But specifically for this problem, my x really stands for my width, so it really should be a w, because in this equation, in the x position is a w, so it's a width. And then the y in this equation is really an a, so it stands for an area. So each number in this table, the x column is going to be the width of the field, the y column is going to be the corresponding area, and the area is going to be in square meters because the fence lengths are in meters. So now I'm going to get the y values, and how I got the y values, I was always lazy. So I'm going to take this function and go y equals, clear out this stuff that's in there. I go 2500. I don't have a w, so I'm going to go x minus x squared. And then remember, we have to set the window to accommodate this. So I'm going to go window, x equal to 0, x equal to 2500. I know the y's are cruddy numbers, but I don't care that they're not so good. I don't really need to see the graph to answer the question. I just need to be able to get the values computed. So now I'm going to go second calc value, type in 0, and it says if the width is 0, well then area is length times width, and if the width is 0, it doesn't matter what the length is, 0 times something is 0. Similarly, if the widths are 2500, then you'd have two 2500 meter widths, you'd have 5,000 meters of width and no meter of length, and you'd get 0 for the area, and that's going to also be 0. That's definitely not my absolute maximum. And then the last one, when I plug in 1250, I get 1,562,500, and that's square meters. So 1,562,500 square meters. I just figured out that I could do all these values at once without having to keep going second calc value. So I look at my table here. This is going to be the point that I'm going to be looking for, because these aren't the maximums. I'm trying to find a maximum. So the value of width that leads to the maximum is 1250. And because I'm building a length and the units are meters, I'm going to say it's 1250, and then either write a symbol for meters or a word for meters. Part E, find the value of the length that leads to maximum area. Well, I know that length is 2500 minus w, so I'm going to go length is 2500 minus w, which is 1250. That I can do in my head. That's 1250. So the length is going to be 1250 meters as well. So it's actually going to be a square, but a square is a rectangle. And then there's two ways to get the area. I can multiply the length times the width. So I went to my main screen, because area is length times width. I know the length is 1250 and the width is 1250, and you get that 1,562,500 square meters. Or if I realized that my table, it already gave me the area, I didn't even have to do that computation. I could have just stole it from my table. So for part F, the area is 1,562,500 square meters. I'll write this as m squared for meters squared. The first couple problems I think are the nicest problems because they fit perfectly with what we did in the last section. There's a few problems in here where the domain isn't so nice, and then maybe we need to look a little better at the graph to figure out exactly if the maximum that I'm getting is really the maximum, or the absolute maximum, or not. So that's problem 2. Your problem 1 is just an exact copy of my problem 2, except I changed the 5,000 to 1,000. So if you had my problem 2 in your notes, you should be able to do that problem 1. But you may not be able to do problem 3, so I'm going to do problem 3 in a second here. Fixing the mistakes I have on the handout as you do this problem, just to give you a second here. Eventually, I guess you just have to pause these things anyways. All right, so I'm going to move down on now to number 4, and it's a similar problem. I have a campground owner. In this case, my campground owner has 4,000 meters of fencing, and he's going to enclose a rectangular field just like in problem 2. But now, one of this field is going to border a river, so we don't need fence along the river. We're just going to make 3 sides. And I'm going to make W the width, L represent the length, and I'm going to make W be the side or the sides of the fence that are perpendicular to the river, so that we will have 2 widths, so that 2 widths and 1 length need to be constructed. So let me, just like I did with problem 2, draw the picture that's implied by this. So in this problem, I don't have blue handy. We have a river we'll say that's essentially straight, and I'm going to build fencing to enclose a rectangular region again, and I'm only building 3 sides. I'm going to make W the sides that are perpendicular to the river, they're the widths, and L the side that's parallel to the river, and I'm making 2 widths and 1 length. Just this is the picture that we need. And just like in the last problem, I'm given just a little bit of information so I could come up with an equation. For what I have to build here, the perimeter of the amount of fence that I have to use is 1 length plus 2 widths, as opposed to 2 lengths plus 2 widths, because I'm only building 1 length. And this 4,000 meters, because it's a linear and not a square unit, represents the perimeter. So this is going to be 4,000 equals L plus 2W. I also know that the area of this is a rectangle, and the area of any rectangle is a length times width, regardless of what I'm doing in terms of constructing. This rectangle that I drew, it's a rectangle. This side is still a length. I'm just not making some fence on this side, but it's still a rectangle. Its area is length times width. I'm going to need that in a bit. So this is the information that I can generate from the first little paragraph. And now I'm going to move on. Just like in 2a, I need to write an equation for the length. To write an equation for a length, I need to take this equation and solve it for L. And that's easy to do. I'm just going to subtract 2w from both sides. When I do that, I get length equals 4,000 minus 2w. It's almost easier in this problem to do that step than it was in the last problem. So now we'll move down, and the questions are going to be similar. So now I'm going to write an equation for the area. Well, again, area is generally length times width, but that's not going to do for this problem. So instead of writing length times width, I'm going to put 4,000 minus 2w in for the length, and I'm going to leave the width alone at the width. So that's going to give me, if I clear the parentheses, area is 4,000 w minus 2w squared. So I'm done with part B. On to the domain, and I want to write the domain in the form some number is less than or equal to w is less than or equal to some number. Well, I know that the widths have to at least be 0, so I'm going to write 0 is less than or equal to w. And I have 4,000 meters of fencing. If all I did was build 2 widths, they at maximum could be 2,000 each. So 2,000 is going to be the maximum of that each width could be, because if I build 2 of them, I've used up all my fencing. All right, so I'm done with that part. And now I'm going to find the maximum. And how do I find a maximum? Well, if I have a nice closed interval like this, I do just like I did in section 4.1. So I'm going to take my area equation. My area equation is 4,000w minus 2w squared and I'm only allowed to look at this with w between 0 and 2000. I'm going to take the derivative, find a critical number. So a prime equals 4000 minus 4w. Set my derivative equal to 0. 4000 minus 4w equals to 0. Add 4w to both sides. I get 4000 equals to 4w. Divide both sides by 4. I get 1000 equal to w. So my critical numbers are the numbers I need to check are 0, 2000, because those are the edges of the domain, and 1000, because that critical number is between the values that I need. So now I'm going to get the y's, and just like in the last problem, the x's are the widths that I'm constructing. The y's are the area that I get if I use those widths. The first two should be 0 again. Let me break out my calculator. I'm going to put in y1 the area function. So in for my y1, y equals clear. I go 4000 x minus 2x squared. My window needs to go from 0 to 2000. I don't care about the y so much. I don't need them. I do graph, and now I get my values. So second calc value, type in 0 and hit enter, and I get 0 for the y. And then type in 2000 and hit enter, and I get 0 for the y. And then type in 1000 and hit enter, and I get 2 million for the y. So my goal is to find the maximum area, and that's of course has to be at that point. So this says you get the maximum area that you can enclose is 2 million square meters. That happens when the width is 1000 square meters. So I have almost the rest of everything that I need. So as I go to do my answers for part D, find the value of w that gives the maximum area. It's going to be w, our width, equal 1000 meters. The other thing that I could answer, find the maximum area. The maximum area is area equals 2 million. And this has to be square meters because area is always square units. The only other thing I need to stumble through is the length, and that's not particularly hard because I'm going to go length is 4000 minus 2w. So length is going to be 4000 minus 2w, so minus 2 times 1000. That's going to be length equals 4000 minus 2000, and that comes out to 2000. So my length is going to be 2000 meters. And if you multiplied the length times the width, you'd get the area, and that's perfect. So that's everything for problem 4. Now you get to do problem 3, which is essentially the same problem. There isn't hardly anything different in my problem 3 from my problem 4 and your problem 3 they're the same problem for, other than there's just a 1 number difference. And always, when I do word problems and put them on a test, it's always, always, always going to be the case that my test word problems are just like one of the word problems that we've done on the homework, just with a number change. So, this whole copy will make its way onto the test, except instead of having 1000 there, we'll have a different number if this word problem makes it onto the test. All right, so we have 4 problems left, and they're essentially the same problems, and I think they're a little bit harder than the first problems, maybe because I'm not that visual and I'm not maybe that gifted at drawing what needs to be drawn. So let me try to go through the initial paragraph. So basically, we're going to start with a square piece of cardboard. So an open box with a square base is going to be made from a square piece of cardboard. So what we're going to have is I don't know if I can even draw a square, but this is a square piece of cardboard, and we'll imagine that each of the sides are 12 inches and what we're going to do is we're going to cut a square from each corner that is x inches by x inches. And we take those and cut them out and throw them away, then I can fold this up on, so now I can fold it up along this line, fold it up along this line, fold it up along this line, and fold it up along this line. And all these sides, when you fold them together, they'll make essentially the bottom of an open box. So they'll make an open box, a box without a top, essentially. So I'm going to fold these, fold this up, fold that up, fold that up, and fold that up, and you're going to get a box without a top. So this is an open box with a square base, is to be made from a square piece of cardboard that's 12 inches by cutting out a square X by X inches from each corner and turning up the sides. This is the picture of what we're going to do, and what we're creating is a box, and a box has volume, and this is what we're going to be focusing on. Let me focus on the box and the volume. Let me focus on the sides of the box. I can't draw that. I don't have a box handy. So when I fold this side up, this box is going to have a height of X. I wish I could. Let me just maybe try to do that with this with a square piece of paper. I don't know how good this is going to be, but it can't be worse than what I'm about to say. So this is essentially a square piece of paper. So we'll pretend that this is the square piece of paper that I started with. And what I'm going to do from this square piece of paper is from each of the edges, I'm going to cut out. So this whole thing is supposed to be 12 by 12. And what I'm going to do is I'm going to cut out an X by X square from each of the corners. I'm physically going to do that. I didn't really draw X by X squares, but they randomly are X by X. Now I'm going to cut these out. So this is what the diagram says that we're doing. So one of them's gone. 2 of them are gone. 3 of them are gone. And then 4 of them are gone. So this is exactly what the instructions say that we're doing. We're starting with a 12 by 12, essentially, piece of cardboard. This wasn't quite 12 by 12, but close enough to 12 by 12. And then what we're going to do is we're going to take each side and fold it up. And what it's going to do is it's going to create an open box, at least something that resembles an open box. So I'm going to have this open box that I'm creating. This is what the instructions say. And when we're dealing with this box, we're going to be asked about the volume of this box. In a volume, we need to have 3 separate lengths to find the volume. And so I'm going to need to know the length of this side, the length of this side, and how tall it is. So I need to come up with numbers that explain, numbers and letters, what the length of this side is, what the length of this side is, and what the height is, because that's going to be the volume of the box that I'm creating. So let me try to talk you through that on my diagram. So these sides right here, all these X's, they get turned up, and they're the height of my box. So this box has a height of X. And then this side right here is kind of like that side. I have to say what its length is, and it's real easy to say what its length is because the whole side started off as 12 inches and I made 2 X-inch cuts. So this side, what's left is the 12 inches that I started with minus the 2 cuts that I took away from it. And the length of this side right here is going to be 12 minus 2x. So I have 2 sides of my box. It's x high, it's 12 minus 2x in this direction, and then I have to find out what its length is in this direction, and it's the same deal. This side was 12 inches. I made 2 x-inch cuts from it. It's also going to be 12 minus 2x in this case, maybe width we'll call it. So the box that I'm creating, it has a height of x, and each of the sides of the base, are they the same size because it's a square, are going to be 12 minus 2x. My figure really doesn't look like a square, but it is what it is. So the dimensions of this the bases are 12 minus 2x by 12 minus 2x, and the height is x. For the bases, I need to call one a length, one a width, one a height, or one a length, one a width, and the x is the height. And in general, when we create a box, whether it has a top or not, the volume of a box you get by multiplying the three different lengths. So it's really, we say it's length times width times height. The x is the height, and these are interchangeably as the length and width. Just like with a rectangle, you can interchange the length and the width. So the box that I'm constructing, its volume is going to be 12 minus 2x times 12 minus 2x, and then the height is h. I'm going to go ahead and clear these parentheses because it's probably going to be handy. So all I've done so far is I'm just going through sketching a diagram that models the problem. This is part A. And because I know we're going to worry about the volume, I'm going deeper, and I'm kind of stepping into part B, write an equation for the volume. So this is my diagram. That's my answer to 6A. When I move down to 6B, well, I already kind of started doing that. My volume is 12 minus 2x times 12 minus 2x times x, where x is the length of the cut in inches that I make. Eventually, I'm going to try to find, probably the maximum volume. I need to make this suitable for a derivative, so I'm going to get rid of these parentheses. So I'm going to FOIL the first two parentheses, and I'll worry about this x later. So I'm going to make these two parentheses go away by FOILing. First are 12 times 12, which is 144. Outers are 12 times minus 2x, which is minus 24x. Inners are minus 2x times 12, which is minus 24x. Lasts are minus 2x times minus 2x, which is plus 4x squared. So that gives me volume equals 144 minus 48x plus 4x squared times x. Now I'm going to multiply through by x. I'm going to get volume equals 144x, multiplying that by x, minus 48x squared, multiplying that by x, and then plus 4x cubed, multiplying that by x. That's the equation for the volume that'll be easiest to take a derivative of, and that's what I'm going to write for my answer to part B. My equation for my volume is going to be volume equals, and I'll write this in a better order. I'm going to switch the 4x cubed and the 144x. So I'm going to write 4x cubed minus 48x squared plus 144x. So there's my volume equation. What's the domain for this? Well, if my initial cardboard is 12 inches and I'm making cuts x by x inches, 0 would be the smallest. I couldn't do a cut that's less than 0. That would be doing no cut at all. And if my cuts were 6 inches, they'd cut the whole sides up. So I couldn't make a cut, because I'm making 2 cuts, I couldn't make a cut bigger than 6 inches because I have to be the same size. 2 6-inch cut would cut the whole piece of paper together. So I know the maximum cut I can make is 6 inches. And quite honestly, you couldn't do 6 inches because you would be cutting and be left with nothing. You really, literally have to do bigger than 0 and less than 6. But for our purposes, we'll say the cuts have to be somewhere at least 0 and less than 6 inches. But I'll put the or equal to just to make it fit with what we've been doing. So now I have a volume equation, I have a domain, and I want to maximize. I want to find the value of x that maximizes or makes the volume the largest. How do I do that? Oh, I take the derivative, create a table, and find the value. Now this, I should probably say I think it's going to be an ugly number. I might have to improve my question and say round x to 2 decimals, because I think I'm going to need the quadratic formula, and I don't want a quadratic formula answer for this problem. So the initial volume function I came up with, volume is 4x cubed minus 48x squared plus 144x. I'm going to take this derivative, so volume prime is going to be 12x squared minus 96x plus 144. Now I get the critical number. I'm going to go 12x squared minus 96x plus 144 equals to 0. I think all these numbers are divisible by 96. I meant by 12. I don't know that for a fact, but 96 divided by 12 is 8. So I'm going to factor out a 12. When I factor out a 12, I get a positive x squared, and then 96 divided by 12 is 8, so I'm going to get minus 8x, and 144 divided by 12 is 12. That actually factors, doesn't it? It factors into x minus 2 times x minus 6, I think, because yeah. Well, that's really nice. So I don't have to modify my instructions. This is coming out amazingly nice. So now I have my derivative factored and set equal to 0. I'll set each of the factors equal to 0. I'll go 12 equal to 0, x minus 2 equal to 0, x minus 6 equal to 0, where x is the length of the cut that I'm making. This one gives no solution because it doesn't have an x. This one gives a solution of x equal to 2. This one gives a solution of x equal to 6. I'm going to make a table. And on my table, I'm going to put 0, 6, and this critical number because it's between 0 and 6, and that 6 I already have there. I don't need it again. The values I'm putting in this column are the x's, which is the length of the cut. The numbers I'm going to get out are the volumes of the box that I get when I make that cut. So now to get my y values, I'm going to enter this function in my y1. I'm going to make my x min 0, my x max 6, and I don't care about the y's in this section. So I'm going to go y equals, and then 4x up arrow 3 minus 48x squared plus 144x. And then window x min 0, x max 6. I don't care what the graph looks like. I can answer the question without seeing the graph, and I won't fuss and take the time to do that. So second calc value, type in 0. If I don't make a cut, I can't even get a box. It's just a flat sheet of paper, so it has no volume. Similarly, if I type in 6 in his equals, that's also not making a cut. You get no volume. Now when I type 2 in hit equals, I get 128. That's the best cut. A 2-inch cut is going to give me the best volume, and the volume is going to be 128. Because the sides are in inches, my volume has to have inches in it, and volume always has cubic units, so it's going to be cubic inches. So the kind of what I'm shooting for in part D, the value of x that makes the volume of largest, the cut needs to be x equals 2 inches. And then for part E, what is the volume? The volume is 128, and it's going to be cubic inches. Probably should have read cubic inches or made a symbol for that, but I could have written IN cubed for cubic inches. So that's problem 6. Your problem 5 is a duplicate of problem 6. So pause the video and do that. If you're good with doing number 5, you can do number 7, because number 7 is exactly the same question, except maybe I changed the top a little bit to not have as much detail as the top for question 5 does, but it really is the same problem. So I'm going to do problem 8 if you can't do problem 7 and try to make the connections. I just try to word it a little bit differently, but it's really the same problem. So problem 8, again, it's the same problem worded maybe how you might see it worded more if I wasn't trying to walk you through the problem so nicely when I word the problems. So an open box is to be made by cutting a square corner out of a 30 by 30 inch sheet of metal as opposed to cardboard. So my diagram that models the problem is I'm starting with a 30 by 30 inch piece of metal. So I have a nice square piece of metal that is 30 inches on all 4 sides. So it's 30 inches by 30 inches by 30 inches by 30 inches. And just like in problem 6, I'm cutting a square corner, and I'm going to call that square corner an x by x corner. Exactly the same diagram, just it's just worded a little bit different just to get you used to seeing different presentations of the same problem. Same picture. I'm going to cut those out and fold those up. And what I'm going to be left with is this side's going to be 30 minus 2x after you fold it up and cut it up. This is going to be 30 minus 2x. This is going to be 30 minus 2x. This is going to be 30 minus 2x. So the base of my box is going to be 30 minus 2x by 30 minus 2x, and the height are going to be these x units. So this is the best diagram I could do in 2 dimensions, and I can't draw in 3 dimensions. So this would be considered a diagram. That's my answer to part A. For part B, the volume, it's going to be the volume of the base, which is 30 minus 2x times 30 minus 2x times the height. This one's going to be nasty, I think. So 30 minus 2x times 30 minus 2x times x. I'm going to pull out another sheet of paper and get this cleaned up. And I'm expecting eventually to get a horrible number, but maybe I won't here. So FOIL these parentheses. 30 times 30 is 900. 30 times minus 2x is minus 60x. Minus 2x times 30 is minus 60x. Minus 2x times minus 2x is plus 4x squared. I might as well write that in a nice order and combine like terms. So I'm going to get 4x squared minus 120x plus 900. Multiply through by this x that's over here, and I get volume equals 4x cubed minus 120x squared plus 900x. So there's my volume equation, and that's what I'm going to write for answer for part B. So for part B, volume equals, even though what's above it is correct, I couldn't really take a derivative that well from that. So 4x cubed minus 120x squared plus 900x. Part C is the domain. This piece of metal is 30 by 30. The smallest cut I can make is 0 inches. And the biggest cut I can make is 15 inches. So I'm making 2 cuts, and if I made 2 15-inch cuts, that's all the metal I have. So now I'm going to have to do some derivative work to find the answer to part D. Because in part D, I'm trying to maximize the volume. And when I maximize the volume, I'm going to need critical numbers along with the endpoints here. So my critical numbers are the 0 and the 15, which are the edges of my domain, and what I get when I take the derivative and set it equal to 0. The derivative is going to be 12x squared minus 240x plus 900. I'd like to factor out a 12 again. I don't know if 12 goes into 900. Yes, it does. So 900 divided by 12 is 75. So I can factor out a 12. So V prime equals 12 times. When I factor out a 12 there, I'm left with just an x squared. And then 240 divided by 12, when I factor that 12 out, you get 20. So it's x squared minus 20x, and then plus 75. I can factor that, but I'm going to pretend that I couldn't factor that because it does factor. I'm going to set my derivative equal to 0, so I'm going to go 12 equals x squared minus 20x plus 75. Set it equal to 0. That's going to give me 12 equal to 0, and x squared minus 20x plus 75 equals to 0. This factors, I'll pretend you can't factor because it's a little tricky factoring. If you have a quadratic equation equal to 0, you could use a quadratic formula if you can't factor it. So I'm going to pretend I couldn't factor it. I'm going to go a equal to 1, b equal to negative 20, c equal to 75, and then I have to use the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. So I'm going to get x equals negative 20 plus or minus the square root of negative 20 squared minus 4 times 1 times 75 all over 2 times 1. I'm going to clean this up. Negative 20 squared is 400. And then 4 times 1 times 75, I'm doing it off the screen, is 300 minus 300. and this double negative turns into a positive. So this simplifies out to be x equals 20 plus or minus the square root of 100 over 2. The square root of 100 is 10, so you get x equals 20 plus or minus 10 over 2. And I need to make the two problems up there, so x is 20 plus 10 over 2, and x equals 20 minus 10 over 2. This one is 30 over 2, which is 15. This one is 10 over 2, which is 5. So those are numbers that I have to consider for my volume, because the volume domain is between 0 and 15. So now I'm going to create a table, and I'm going to have 0 in my table, 15 in my table, 5 in my table. Oh, and that 15 again, I don't need to put it in there. So my x column is going to be the cut in inches. The y column is going to be the volume in cubic inches. And I'm taking the numbers from my domain, 0 and 15, putting them in the x column just like we did in the last section. And in addition, I'm throwing this 5 on there. And I'm going to get my y's by using the original function, putting that in my y1, make my window from 0 to 15, and get the values for the y's. So now I'm going to just break my calculator in. Y equals clear 4x up arrow 3 minus 12 x squared plus 900x. Enter. Window x equals 0 to 15. Graph. Don't need to see the graph to answer the question. I just need to be able to get the values. So now second calc, value, type in 0 and hit enter, and I get 0. Type in 15 and hit enter, and I get 0. Type in 5 and hit enter, and I get 2,000. So clearly, making a 5-inch cut is going to be the optimal cut, and it's going to give me a volume of 2,000 cubic inches. So now I'm ready to answer the question. The question's find the value of x that makes the volume the largest. It's going to be x equals 5 inches. And then the volume is going to be this 2,000. And it's going to be cubic inches. And I'm just going to write that with the symbol for cubic inches. So problem 8 really is just exactly problem 6 again. I just wrote up the words a little bit different because not every problem is always going to be presented exactly the same way, even if we're asking you to do the same operations. So with that, hopefully you can do number 7, and that's all there are. There's just 8 problems in this section. Nice, just nice one-part video, and we're done. All right, so we've got a few more sections to do. 2 of them are word problems, and again, I tried never to make the word problem sections, the things that are going to kill you. So just bear with it, and you should be able to do these just fine.